So our next speaker is Brent Werness from University of Washington, talking about convergence of discrete holomorphic functions on non-uniform lattices.
Thank you very much for the introduction, and I'm very happy to be here. I was very pleased to be invited. And I'm also particularly pleased to be able to come here and talk today because I'm actually the first of Greg's students to give a talk at this workshop, to the best of my knowledge. And so, I don't know, just something I like. Okay. And anyway, yeah, as many other people have said, let's just get on with the mathematics. I mean, sort of fitting. So I'm going to be talking about convergence of discrete holomorphic functions on non-uniform lattices. And so just to say a few general words before I leap in with anything is that this is all part of sort of, to see how this sort of fits into a lot of different talks that have been discussed here, is that this is all sort of part of the program to try and understand sort of the random processes on random surfaces, in particular to try and develop the tools required in order to prove results along the lines of convergence of SLE to, loop erase random walk to SLE2 on a random surface appropriately selected. All right, so here's just a quick little history of what's going on with these discrete holomorphic functions, because they've been around for a while now. And so starting in the 1920s, they were sort of studied just for their inherent nicety. I mean, just you studied them because they are connected electrical networks or because you want to discretize Cauchy-Riemann equations. And then also coming up more recently has been this whole circle packing school. And most importantly to us, more than just these circle packings or these electrical networks, we care because when you study these processes from statistical mechanics, discrete holomorphic functions just seem to fall out quite often. And so I've listed a few names here. Lawler, Schwab, and Werner for the first sort of convergence results to SLE. They use these methods, as Dubida explained this morning, of sort of these holomorphic martingale observables. Shelcock, Smirnov, people like that, they worked a lot on sort of these other sort of proofs for the Cartes formula, things along the lines of that, and Emile Capin. So there's many, many people who have produced many nice results using discrete holomorphic functions on various lattices. And then just as a sort of little side remark that I find kind of interesting is that there's an entire extra branch being developed in the modern time as well by computer scientists, numerical analysts, working Markov, Schroeder, Pinkel, many people at Berlin. And they're sort of producing interesting results as well along these same kinds of lines. Okay. So now, just to sort of motivate for us here, as we sort of saw before, if you want to show that some discrete statistical physics model converges to some nice scaling limit like an SLE2, well, there's one technique that certainly has proven to be the most useful, I think, overall. And that is you want to identify some sort of discretely harmonic or holomorphic function associated to your random model, and then show that you have some sort of nice enough tightness that you can take scaling limits to get that it becomes an honest holomorphic function, thus prove convergence. And so, just because I guess it's Greg's birthday, I should give one example just to sort of explain very briefly. So I give SLE2 and loop erase random walk. And so here's the discrete harmonic function. I just sort of drawn it here. Here I took a random walk and erased the loops. The harmonic function they used in that original paper is the probability that you're on the path before the loop erasure. And they show that that is a harmonic function and that it has a limit, and that was sort of one of the technical cores behind that convergence paper. Okay. Then in parallel, beside these statistical physics things, there's also this random surface business going on these days. And so just, again, as many people have talked about, I just want to say a few words here, is if I hand you, say, a bag of 100 quadrilaterals, and I tell you, tape it together in such a way that you get a surface which is homeomorphic to the sphere. What does that thing look like? Well, the way that you answer that question depends a lot on what sort of school of thought you come from. So many people like Legal and Mirmont, they say, well, when we glue together these 100 rectangles or 100 squares, we look at this and we see a metric space, and so we try and take limits as a metric space. People like, I guess, Polyakov in the 1980s, Duplantier, Sheffield, Miller, they take it and they say, well, we're going to glue these things together. We get something that looks like a Riemann surface. We want to understand what that limiting Riemann surface object looks like. And many others have sort of gone along and said, like, well, what if you take random objects? Like, look at what happens if you take a percolation exploration on, say, a UIPT or something like that, trying to understand random processes on these random surfaces. And sort of the idea behind all these things, and I mean, Jason gave an extremely nice talk sort of with this very new and very beautiful connection between the first two here, and well, sort of all three even. Sort of the idea is that you want to say, like, how are these things interconnected, and how can we sort of say what's going on in all these things at once? Okay, so now we have these two ideas here, right? If we want to go through and do these random processes on things, we need to go through, oh, yes, okay. in order to do these random processes on various surfaces or various lattices, what you need tools for proving convergence of discrete holomorphic functions to their continuum counterparts. That's sort of the core of all these convergence results towards SOV. And if you're going to deal with random surfaces, well, you're going to need that convergence result to include the kinds of lattices you get if you work with random surfaces. And well, what does that mean? Here are some random surfaces. So over here, this is just a few hundred quadrilaterals, not a very big surface here. And so I just picked it at random. And it's embedded in a way that attempts to be isometric. So this tries to be sort of as close to an isometric embedding as you can get into R3. And well, on the right, again, we've seen many pictures like this in these talks so far as well. What we have there is we have the circle-packed version of this exact same surface. And there's one very sort of immediate thing that you see that jumps out at you, which is that when you take this surface and you circle pack it, so you try and produce a lattice that lives on one of these, on just like a sphere in this case, what you see is that you have this enormous difference of scale. So I mean, it's an open question, but one that's well believed, I think, that the largest circle should go to 0. So these big circles, they'll eventually vanish. In this case, the hope is that they eventually vanish. We don't know. But what I want to sort of point out here is that you have some enormous circles and some itty-bitty circles, difference of orders of magnitude, like hundreds of orders of magnitude. And so if you want to prove convergence of discrete holomorphic functions to continuum ones, it better be the case that whatever sort of theorem we're working with, and sort of we want to have these tools to work with these things, I guess to put it in a better way, we better be able to handle lattices where there's an enormous disparity in absolute size between different quadrilaterals. And that's what we're going to show here today, is I'm going to produce a result along these lines. So we wish to produce this thing. And well, just to give us a distinct goal here, I want to produce a convergence result that's robust enough to hold on lattices that are produced, say, by circle packing at least some random surfaces. And so what I'll be able to show, a result that if you have a sequence of lattices obtained by circle packing bounded degree things, then you can get convergence. That'll be one corollary. Well, as long as the size of your largest quadrilateral goes to 0. Again, that's always looming in the background. Okay. So now just a quick background. I mean, again, most everyone in the room will sort of understand these notions, but I want to sort of make sure that's here. So if we want to go through discrete holomorphicity, and I guess what I'll say first is that this is not the definition you want to take, but it sort of will lead us there, is that, well, you want to go through, and you want to define what it means to be a discretely holomorphic function. And so you say, well, holomorphicity means that you have this one limit existing as a complex limit. That sort of means you can take it independently along real and complex axes, so you just discretize it like this. This is a good guess. And you get sort of just this natural guess as what it means to have a function that's discretely holomorphic. This immediately has some problems. In particular, there's basically no symmetry here, right? Because we sort of take a difference here compared to a difference here, and if you rotate the lattice, there's no reason at all to believe that there's something being discrete holomorphic like this. If you rotate it by 90 degrees, it doesn't need to be. So that's what I'm saying here, is that if you have one of these discretely homomorphic functions by this definition was explored in the 1920s as well, because it's sort of the most natural guess. If you have I guess maybe I should have written down an explicit example, but I think it's probably clear enough that these things could exist, is that if you have something where this equals, this difference equals I times this difference, doesn't it all imply that this difference equals I times this difference? Okay. And so this is all, of course, observed in the 1920s, and it's been sort of worked out, so I guess I can just tell you what happens next, and just tell you the good way to get around this problem, is that you look at the diagonals of your quadrilateral instead. And so you declare that, well, a function is going to be discretely holomorphic if the difference along this diagonal divided by that thing equals the difference along this diagonal divided by that displacement there. Or equivalently, just the differences are I times those differences over there. All right, and this has the nice property that if you have a function that's discretely holomorphic and you sort of rotate it by 90 degrees or what you want to say, it remains discretely holomorphic under this definition. Just because the diagonals, they might sort of change where they point, but they remain the diagonals. This definition also has a very nice feature, which is that, well, while the first one really only made sense for squares, right, because you had to pick like what the lower left corner meant and things like that, here, this thing makes perfect sense if I just draw any quadrilateral at all. So if you take any old quadrilateral, we can define what it means to be discretely holomorphic across that quadrilateral just by saying the difference of the function on these two diagonals is equal, sort of the difference quotients on these two diagonals are equal in the complex sense. Okay. And this is just a little comment here because it makes the theory technically quite a bit nicer. Throughout everything I'm going to be talking about here today, we're going to be dealing with quadrilaterals with orthogonal diagonals. And so, I mean, this just means, well, it has a number of consequences, but I mean, it's the one where all the properties you expect a discrete holomorphic function to have do get carried over in this setting, whereas if you don't have that requirement, there are some issues. Okay. So just a note on terminology, just because I'm going to say some things without necessarily defining everything that I mean, is that, so if I talk about, like, you know, say a simply connected quadrilateral lattice, that just means that if you union the quadrilaterals, it's simply connected. So in general, if I say anything topological, I just mean union together the quadrilaterals. That'll give you some domain, then apply that topological term. And also, if I ever say anything about quadrilaterals, then I just mean that thing holds for every quadrilateral in the lattice. So like if I call something a rhombic lattice, the lattice where everything's a rhombus. Okay. So now, I've sort of told you what these discretely holomorphic functions are. And well, for the work that we're going to be talking about today, we're going to not work necessarily directly with discrete holomorphic functions, but we're instead going to work on discrete harmonic functions and talk about sort of Dirichlet problems of discrete harmonic functions. I mean, this is a restriction certainly, but in many of the cases that we've dealt with, what sort of ends up being the case, so say in the work of Smirnov and others, that you can sort of say have your discrete harmonic function satisfy certain boundary values, just doing the Dirichlet problem on the real and imaginary parts, and then if you have limits of those, you'll be fine. And so this will at least be a useful case. So we're going to be dealing with these discrete holomorphic functions on some quadrilateral lattices. We're going to fix some boundary values, and this, I just want to put this definition down here just to accentuate this term, this fact here, which is if you want to try and do the solution of a discrete Dirichlet problem, we want to have it converge to the continuous one. Well, maybe I'll quickly draw a picture of what's going on here. So if you have some continuum domain, and you want to approximate it by quadrilaterals, or whatever, it's not necessarily going to be the case that your boundary is at all close to what you're starting with. And so it better be the case that whatever you mean by solving the Dirichlet problem with given boundary values, it better be the case that your boundary values make sense when you're sort of away from the actual boundary of your set. So just for sort of technical convenience here, but something that's important, is that we'll ensure that our boundary values live on all of C. So, you know, we want to say our boundary values will in fact be a C1 function on C. And we're just going to sort of say that you just fix it on the boundary of that and you take your limits. Okay. So now, what are the modes of convergence here? Because I'm saying things, this lattice converges here, you want this to converge, and it's clear when you're talking about a square lattice what you mean. Definitions become a little bit trickier when you're talking about just arbitrary piles of quadrilaterals. But again, this is actually a little bit sort of standard terminology, but I want to make sure it's sort of known here. That what we want to do is we want to say that we have a sequence of quadrilateral lattices converging to some simply connected domain. And well, the case where it's sort of interesting is when your simply connected domain is sort of weird, like say the slit disk here. And well, what you want to do in order to make sure that everything works out, so you want to be sure that you're working with the boundary values along the slit as well, is you want to say that your lattices converge to this domain as long as the Hausdorff distances between the boundaries go to 0. So that sort of ensures that your lattices follow along here, and that the maximal edge length tends to 0, so that your quadrilaterals, you know, you don't have any quadrilaterals that stay macroscopic in the limit. All right, so that's what we mean when we say convergence of the domains. Convergence of the functions, we just mean the sup norm sense, but the sup norm where you restrict to the images of the vertices of your quadrilateral. So no extension, we just say that your functions are converge if whenever you restrict to the vertices of your lattice and compare the limiting function to the one on the lattice, that goes to 0. All right, and so now we know what it means to have these discretely holomorphic functions. We know what it means for domains to converge. We know what it means to solve the Dirichlet problem, and we know what it means to have the functions converge. So now the question is, when do we know that this convergence holds? So right, if we have a sequence of lattices that converge to a domain, do we have that the solution of the Dirichlet problem converges to the solution of the Dirichlet problem in the continuum domain? And this is a nice sort of area that's had many, many results along these lines. So first off, the historical ones, there's work by Courant, Friedrichs, Louis, and Lusternik in the 1920s. And they proved it just for the square lattice. They said, if you have a square lattice and you take this definition of discretely holomorphic, then you can go through and check that everything works out the way you expect it to, and you get convergence of the solutions to the discrete Dirichlet problem to the continuum one. Then, much more recently, sort of like I said, there was this revival amongst probabilists at least, result by Smirnov and Shelcock, extended this sort of thing for rhombic lattices, or isoradial graphs, equivalently. And then, much more recently, Skopenkov in 2013 proved something along these lines, where it was, and I'll be more specific about what that result said in a minute, but it basically says that you have some collection of orthogonal quadrilateral lattices, and you have some condition on global geometric control. So something that says, that there aren't too many quadrilaterals in any little section. Then you also have this in a great degree of generality. But sort of the point for us here is that we are motivated by these questions coming out of random surfaces and random geometries. So if you want to get convergence on random geometries, it's just not enough to have these things that have this global geometric control that says, that in some region there's no more than, say, 100 quadrilaterals. You need some sort of thing that says, well, as long as your quadrilaterals themselves are not too distorted, then you're fine, no matter how tightly they pack themselves in little regions. And so that's what we're going to be doing here. So let me now state what my main result is. Well, so first I need to say what I mean by this local geometric control. So if you give me a quadrilateral, I'm going to call it k round if the ratio of all lengths of the edges and diagonals are bounded above by k, so you never have drastically different lengths, and all the angles are bounded below by 1 over k, so you don't have any very, very narrow quadrilaterals. So these things are quadrilaterals that are sort of generically not bad. So they're not like an example of a bad quadrilateral. It's something like that guy, or I guess that's a little bit too tightly packed there. That quadrilateral there. This one's even kind of an interesting one because this is, in fact, if you look at it, an orthogonal quadrilateral where the diagonals are the same length. But this is the example of the sort of thing that we do not want to deal with. These are extremely degenerate and sort of make things extremely hard to work with. All right, but if you just fix this condition of k round, then unfortunately for sort of doing probabilistic work, for the proof that I'm going to give here and the theorem that I'm stating, you're going to have to fix 1k for all time. So things will have to be uniformly k round when you take your limit. And so we fix our k, and now we take our sequence of k round orthogonal quadrilateral lattices that are approximating our domain. And we fix, as I said, some C1 boundary values, which is a C1 function on all of C. And we consider the sequence of solutions to the discrete Dirichlet problem. And what we're going to show here is that these converge uniformly to the solutions of the Dirichlet problem in the original domain. So that all that you need here is this one little local control saying that individual quadrilaterals are not horribly distorted. And if you have that sort of condition, that's enough to say that you have this convergence. So you don't have to worry about square lattices or isoradial or any of these things. You just need to say that individual quadrilaterals are not horribly distorted. Okay. Just for the sake of comparison, here's Skopenkov's result. And so he defined this notion of C uniform non-degenerate, which again had this local component saying that diagonals, that the ratio of the diagonals are bounded above by C. So again, you have this sort of non-local distortion thing. But then the thing that causes problems for any sort of applications to, say, random surface type situations is this second point down here, which says that if you take a bunch of quadrilaterals and you look at a disk with a radius given by the maximal edge length, so you have 100 quadrilaterals, you look at the longest edge, and you lay down a disk of that size, then you have no more than C vertices contained within that disk. So this means that sort of there's a bounded distortion in scale between your biggest and smallest faces. And then the theorem that Skopenkov proved was the same thing here. So the same thing that said if you have only C uniform families, then you have convergence. Okay. So that's sort of our general setup and what it is that we're trying to prove. Let me sort of get in a little bit now into how we go about proving this. So this is a general outline. This in fact is the outline for all the 3 other proofs as well, because it's a outline motivated by sort of the classical sort of continuum analysis work. And so if we want to show that these discrete harmonic functions converge in some sense to the continuum one, let's sort of this 3-step process here. The first thing you want to do is you want to say, well, if I have a sequence of discrete harmonic functions and we know it converges to something, so if I just have this condition to begin with, you want to say, well, that something had better be harmonic. That's a good starting place. Now you know that if it converges, it has to converge to a harmonic thing, because I'm taking this sequence of solutions of the discrete Dirichlet problem, so it better be the case that they converge to discrete harmonic functions. And well, in order to now prove that this thing actually converges, that these things actually do converge, you now have some control over the discrete harmonic functions themselves. And so that comes in 2 steps. The first step is that you prove that the discrete Dirichlet energy is bounded uniformly in terms of the standard continuum Dirichlet energy. So this just says that, what I mean by this is if you take some function in the continuum and you just restrict its values to live on the lattice, then the Dirichlet energy of the thing in the continuum bounds the Dirichlet energy of the thing on the lattice. And well, once you have that, you sort of know, at least intuitively, right, if you have a bound on the Dirichlet energy, this bounds how wildly your function can fluctuate. And so what you want to do is you want to take this and establish an equicontinuity result. So you want to say that if you're given these solutions of the Dirichlet problem, so you have this same collection of boundary values, and you have this now bound on the Dirichlet energy, which sort of stops your function from oscillating too wildly, we want to be able to show that this means that you have then bounds on the modulus of continuity of your function to begin with, and thus sort of Arzela-Ascoli, standard tricks like that, you can conclude convergence. Okay. So now, before leaping into the complexities of what happens in the discrete setting, let me go over sort of the proof that we'll be mimicking from the continuous setting. And so, maybe go back to the outline here. It sort of turns out that these 2 things, sort of the techniques that are being used, that have been used since like 1920, these are pretty robust. Like these 2 steps here. They can handle changes in the situation pretty readily. It's this equicontinuity result that turns out to be the most sensitive. If you want to show that these things converge, this step is the one that sort of generally seems to cause the problems. Or at least it's the one that caused the problems for me. And so, well, let's discuss how such a thing is done. Again, this is just, right now it's in general for sort of things living in the continuum is what I'm going to say first. And this is something you may have even seen like an undergraduate analysis class if they talked about harmonic functions and things like that. But it's sort of, it's the core behind the proof that we're working with here, which is, well, so we want to control the difference of the function between z and w. And I'm going to build this up in a few steps. So I'm just going to take some sort of curve in C. Eventually we'll take this to be part of a circular arc, but right now just consider any arbitrary, say, smooth curve parameterized by arc length. And all we're going to do is just we're going to apply now Cauchy-Schwarz to this guy. So you say, what's the difference between the values of the 2 endpoints squared? Well, it's the integral squared, which is less than or equal to the product of those 2 integrals. Okay. So all I've done is I've just taken my curve, applied Cauchy-Schwarz. And what you see is if you just rearrange this a little bit, you now get that the integral of the gradient squared along this curve is bounded below by the difference in the function at the 2 endpoints squared divided by the length of the curve. Okay. This, like I said, this is all just sort of classical analysis stuff here. And now, what are you going to do? I haven't assumed anything about my function yet, but we want to be talking about what you do with harmonic functions. So now, let's assume that w, instead of just being some sort of arbitrary function, is now harmonic. And well, for a harmonic function, it has this very nice thing, the maximum principle. And so, if we now want to compare the values of z and w, let's assume, say, u of z is bigger than u of w. What the maximum principle tells us is that, well, a harmonic function takes its maximum on the boundary, and so whatever value u of z is, there's something that takes a value at least that big on the boundary. For whatever u of w is, there's something that takes a value at least that small on the boundary. And so if you take the 2 points on the boundary of this ball, connect them up, then you know that the difference between u of z and u of w, which bounds the difference between the 2 points on the boundary, well, you take that arc that connects them, apply the lemma that I had in the previous slide, that tells you the integral along that arc of grad u squared is bounded below by the difference of the values of the interior divided by 2 pi r, well, 2 pi the length of the arc. And then on either side, that's bounded by the integral over the entire ball, which I've written here, and the difference divided by 2 pi r. And so what this sort of tells you is that if your function differed by a large amount here, it would have to do so by placing a certain amount of Dirichlet energy on the ball of radius r around your point. Okay. And now to turn this into a bound sort of that works in terms of our bound on the Dirichlet energy, all you do is you just integrate from norm ZW out to R. So you just integrate this thing over this region. And what does that tell us? Well, maybe let me go back here. On the one hand, we have this expression here that says the integral of the Dirichlet energy on the ball of radius R is something. And so when we integrate that to R, what we get on this side is the Dirichlet energy contained in the annulus between norm Z minus W out to R, which is, of course, bounded then by the Dirichlet energy of the function inside the entire domain. And then on the other side, we have uz minus uw squared. That's the same on this side always. And then just a logarithm coming out. There's some constants here, but I'm neglecting. And so now you just take this expression here, you sort of shuffle everything around, and what you see is that the difference of the function in the interior is bounded above by something involving just the Dirichlet energy and the log of this ratio of this annulus. And now this is sort of a very, very sort of rough and ready sort of estimate here, because, well, notice I've said nothing about the boundary values right now. This is just a statement about harmonic functions. And when working with the Dirichlet problem, you're going to have to somehow take into account what happens on the boundary. And, well, I won't get into that in this continuum setting here. I'll discuss that a little bit more when I'm working on my discrete ways of working with this. But this gives you the idea here, which is that you want to have this annulus, and you want to go through, and you want to bound the difference of the function on the annulus in terms of this Dirichlet energy and the logarithm. The logarithm of the distance between them. Okay. So now let's talk discrete, and here's where things get a little messy, but they kind of have to sometimes. So first off, we need to sort of start developing discrete analogs of everything that we worked with in that argument, right? And so again, this part here goes back to Skapenkov again, or perhaps earlier. So first thing we want to do is we want to define what we mean by a gradient on one of these quadrilaterals. And well, what we have is we have the difference of the function over these two diagonals. And just what the gradient is going to be the complex number that when you dot product it, that's what it's meant by this little circled dot here, because I want to distinguish it from complex multiplication, is that the gradient is the thing that when you dot product it with the difference along a diagonal, it gives you the difference of the function between the two vertices on that diagonal. So if you dot product the gradient against z3 minus z1, you get uz3 minus uz1. Dot product against z4 z2, you get uz4 minus z2. All right, and this, of course, mirrors the property you'd expect a gradient to have. And then the discrete Dirichlet energy is just the sum of the squares of all these gradients times the area of your faces summed over all the faces. And so now just for sort of reference here, because I know a lot of you have worked with discrete holomorphic functions, this definition perhaps seems a bit strange, a bit different from the one that you're used to. And this is one of the reasons that we restrict to orthogonal lattices as well, is that if you restrict to these orthogonal lattices, you can go through and just compute by hand what this gradient has to be in terms of the coordinates of the quadrilateral and everything like that. Write down what the area is in terms of the differences. And what you see is that if you take this discrete Dirichlet energy and you now write it out in terms of the actual coordinates, it's 1/2 the sum over the faces of some constants, these sort of normalization terms, differences of squares of the values across the diagonal. So if you've sort of worked with your harmonic functions and you think about like involving random walks, you want to say that it's just being harmonic means that you're average your 4 neighbors or whatever it is. This is how you make connection to that definition, is that this thing here tells you that to be discretely harmonic, or at least the Dirichlet energy is sort of minimized when your values of the function are the average of the values across the diagonals. All right. So that's our Dirichlet energy. And as I said, I'm going to sort of be working under the assumption of the first 2 bullet points where I gave the outline. Oops. And so I'm going to be working on the assumption here that I have a bounded discrete Dirichlet energy. Again, you can sort of prove that is true in the case that you have this initial this bound from coming from the continuum. And so we're going to try and use this to now get that equicontinuity result, and that's the one that I want to sketch. So how is this normally done? Well, what you do is you want to sort of, again, mirror this argument. So you take your annulus, and you want to find a collection of paths, discrete paths on your lattice, so that they use a disjoint collection of quadrilaterals. And then what you do is you just repeat essentially the same argument, right? Because if you have one of these paths here, so you took a circle, And he said, okay, I'm going to go look in my lattice, and I'm going to find some lattice path that sticks very close to this circle that I'm trying to approximate. And so over here, I have these lattice paths made of diagonals of quadrilaterals. And well, what do is once you have one of these lattice paths that goes across diagonals of quadrilaterals, you can go through and say, well, I'm going to do the same Cauchy-Schwarz argument I did before. I'm going to look at the difference between the values of the endpoints. I'm going to square that difference. And then Cauchy-Schwarz it, and you get it's sort of divided that through by the k here being the discrete length of this path. And that bounds that bounds this sum of differences along there. And recall that from the previous slide, we know that our discrete Dirichlet energy is written in terms of sums of squares of differences across diagonals. And so here we sort of see that we're getting control over the right kind of terms along these paths. Okay. And now what we did next in the continuum estimate is we went through and we said, okay, we found these, well, there we integrate over circles. Here we sort of have these discrete approximations of circles. You want to say that we can now essentially sum this over all the discrete paths out in a certain annulus to get the bound that we want. And the key here is going to be the following to the sort of traditional way of going through this argument, of discretizing this continuum argument, is you want to say that when you're dealing with one of these paths, that since you have this global geometric control, all your quadrilaterals are about the same size, and so integrals along the paths are pretty well approximated by combinatorial sums, and this k here, this combinatorial length, pretty well approximates, well, delta k approximates the geometric length of your path. And then, well, what you do is you integrate this, well, you sum this over R for a collection of disjoint paths, of which you can get many, many, many of them, just by taking the paths to be separated by more than the maximal diameter of a quadrilateral. And so if you just work through it, you'll see what happens is you get the exact same kind of estimate as before. That you can bound the difference of the function in terms of this Dirichlet energy times the log of the radius divided by z minus w. Okay. But now my claim here, which I want to sort of explain a little bit now, is that this will never work for the kind of thing that you want to deal with quantum gravities, with these randoms. If you circle pack, say, a random quadriangulation, it comes down to this vastly differing size of quadrilaterals that you encounter. So it was very important to us that every quadrilateral had about delta worth of length on it and delta squared worth of area on it in this argument that I've sketched here, because we wanted to approximate both the length integral and the area integral using that sort of thing. And well, I mean, first off, this already just sort of makes things quite bad because, of course, if your quadrilaterals are different size, that's just not true. They contribute however big they happen to be. And sort of equally well is you wanted to say that if you're given a smooth curve, you can find a discrete approximating curve where the sums of diameters of the things you're using a discrete approximation is more or less the length of the curve. And in general, for both these bullet points, I've sort of said it verbally already, but we want it to be the case that we can now use combinatorial sums to estimate these sort of geometric quantities, integrals over lengths and over areas. And as I said, we're sort of shot at bullet point 1 here because there's really no way to do that if you have differing size quadrilaterals. Because if you have some sort of very small quadrilateral, even worse, a fairly distorted quadrilateral, it's just not going to be the case that your combinatorial length will tell you anything at all about your geometric length. Okay. And so here I've sort of done the same thing in sort of a cartoon version of what happens when you have very differing, very largely differing sizes. And so I guess what I mean with this picture here is a little bit unclear, is that if you had this thing, you have this quadrilateral lattice, and there's some very, very large quadrilaterals, like these guys down here. Then there's some very, very small ones. And so you have sort of this tension going on here, that if you now do these things so that they're well enough separated that the large quadrilaterals do not overlap. Here I showed them overlapping. If you took them far enough away so they didn't overlap, so you could do these estimates on energy, well, you'd be in trouble just because that's that's a very large separation compared to the size of the smallest square. On the other hand, if you tried to discretize these things to a spacing between them about the size of the smallest square, you'd again be in trouble because now you have massive overlap and you don't know how to take care of that when you're estimating the energy. And so, just in the one bullet point of the idea before I go through and finish off the talk by doing some details, a bit of what's actually going on here, rather than sort of sketching the argument in broad generality, is that what we want to do is, instead of using the energy just coming from this combinatorial sum, the very broad strokes idea is you want to have the energy, you sort of look at the energy contributed to a path weighted by its diameter. I mean, this is of course clear. I've sort of presented the argument in a way that this is clear, but from the other discrete arguments, it's not necessarily obvious this is where you want to go. But so you just want to approximate this linear integral across a circle. So the most reasonable thing to do is, well, you just integrate the Dirichlet energy compared to the diameter of that quadrilateral that you're working with. And then you want to say, well, now that I've gone through and I've done this thing, so this one counts with respect to its diameter and so on, you want to now say that when you take the integral over all r, so now this is sort of a half continuous, half discrete kind of argument that I'm saying here, is that you take your ball of radius r, you approximate by a collection of quadrilaterals, and now you actually integrate in r instead of taking a collection of disjoint paths. And the reason that this will work, this will give us what we want, is that when you consider how much a single quadrilateral will be used, it'll be used in proportion to sort of the number of circles that intersect it, because that's the collection that sort of needs to use that one quadrilateral to contribute to its energy. So in that, when you estimate the sum on the circle, you get that the diameter of the quadrilateral coming in, just because I'm sort of defining that's what we want to compute in bounds. So you get one factor diameter coming from that, and then when you integrate in r, you get another factor of the diameter. And so these two factors together give you diameter squared. And this is where we come back to the condition that I have this k round business. Because what does k round do sort of morally for us here, at least at this point in the argument? It tells us that, well, if you have something and you know that its diameter squared is something, k round tells you that its area is approximately equal to the diameter squared. And so that means that you can change it to an integral over area and do that kind of estimate of the Dirichlet energy you want. Okay. But of course, with this kind of argument, the devil's very much in the details. So let's just start here. So I call this the semi-energy. It just means that if I take a ball of radius r and I look at which faces in my quadrilateral lattice intersect that ball of radius r. So I'm not going to be approximated by a path or anything like that. I'm just going to say, take my ball, it hits a collection of quadrilaterals. That collection of quadrilaterals could be essentially anything. We're going to take those, and I'm going to look at the sum of the Dirichlet, this sort of gradient squared, times the diameter of the face. And I'm going to sum that over all the things that intersect that ball. Okay. And well, again, just sort of leading towards where I'm going, this is how we're going to get our estimate on the Dirichlet energies. We're going to take this fellow, we're going to integrate him over r. Okay. And so, as before, we're going to need to do a little bit of a Cauchy-Schwarz game. And so here I've just sort of written out what that produces exactly in this case. And, well, okay, so some technicality I should have discussed perhaps earlier. Maybe I'll do a little sideboarding on it. Is that there's an annoying issue with this definition of discrete holomorphicity, which is that, so if you have your quadrilateral lattice, here's some little subset of it. I mean, it's going to be very quickly seen that this graph is bipartite. I mean, just you have all even-sized faces here. So you have this natural separation into two subcollections of vertices. Call them, say, black and white. All right. And now if you remember my condition of discrete holomorphicity, or my expression for the Dirichlet energy, or any of these sorts of things, it took the form of difference of the values of the function across this diagonal times the direction of this diagonal equals the difference across this diagonal divided by sort of the difference between the endpoints across the diagonal. And so what we saw, in particular, everything involved only differences of the values of the functions on these endpoints. And so it's in fact the case, and this is one of the annoyances in theory, you can, Stoss talks about this, many people have talked about this, is that if you have a function that's discretely holomorphic, you can go through and you can add any constant you want to, say, all the white vertices, and it remains discretely holomorphic. There's sort of this independence of what goes on in the white vertices versus the black ones. And so when you have this independence, it makes things fairly annoying to work with. And so a little bit of a notation we have here is that I have Q star, this is the vertex set of my graph, And this Q dot business here, this is going to be my graph restricted to only the black vertices. And so this has the effect of if you sort of do your bounds only on the black vertices and you do them on the white ones, you can sort of handle this translational degree of freedom independently. You don't have to worry about that anymore. But okay, so we're going to take any old function. Again, this is just the Cauchy-Schwarz business I'm doing here. And we're going to take a path on the black vertices. Just you go diagonally from black vertex to black vertex to black vertex across this lattice. And well, you consider the semi-energy contained along that path. And again, I mean, since it's just Cauchy-Schwarz, I'm not going to go over this again, how it exactly works out. But what you see is that the sum of the squares of what happens on that thing times the diameter is just bounded below by a different square divided by the length, where the length now is actually the Euclidean length of all the things along the path summed up. So the actual Euclidean length. All right, and so that was sort of component one we needed in our continuum thing. And then component two was that we needed to go through and say, if we take this path, say an arc of a circle, and we approximate it by a discrete path, we need that approximation to somehow reflect what's going on with the continuum path. So we need to make that, we need to be able to bound this sum of diameters of the faces along the path in terms of the length. And so this is sort of one of the, I guess, sort of neat little technical tricks that we've had to do here, is to go through and produce such a bound. So, I mean, let me just sort of first sort of say why this is not necessarily obvious, right? Because what you want to do, what would you do if you wanted to try and prove this? You wanted to say, so you want to say that the length of your curve times some constant that perhaps depends on how round you're forcing things to be, bounds the sum of the diameters of your faces. Well, sort of what you want to say is you want to say if you have a collection of faces, whatever they happen to be, I guess I'm just drawing them here. You want to say that when you consider a path going through these faces, that sort of each time it hits a quadrilateral, it sort of needs to have spent sort of length time about the diameter of the quadrilateral in that face. So that way sort of each face contributes about its diameter worth of length. He sums up to the total length of the curve, and you be set. But this is, of course, I mean, it doesn't take very long to identify that this is completely false. I mean, what stops you from just kind of doing a little something like this? You know, you come along and you maybe just nick the corner of one of these guys. And so you need to know that when you're going through and computing sort of, and you want to try and bound the sum of the diameters, you sort of need to know somehow that's not the case that as you sort of your path wanders along the lattice, it does so only by sort of nicking the corner of every single quadrilateral it passes by. That at some point it actually needs to sort of spend a decent time passing through some quadrilaterals. Okay. And the sketch of the proof is the following picture. Because what this tells you is how our condition of K roundness is going to come into play again. So we have here our quadrilateral. So this is a face. Now I'm imagining that some sort of curve came in, maybe nicked the corner of this quadrilateral and headed on out again. And what we want to do is we want to bound the sums of the squares of the sums of the diameters in terms of the length of the curve. And so when you nick this little corner of the quadrilateral here, you will not spend much time in that quadrilateral. I mean, that's just what it means. But what you want to do is you want to consider all neighbors to this quadrilateral, so all faces that share a vertex. Now, what does K roundness tells us is that if you look at these quadrilaterals that are the neighbors, I did sort of only run one corner here, all of these lengths and all these diagonal lengths that are drawn in dotted lines, they're all comparable up to some constant ck, some constant ck, to the diameter, say, of our original quadrilateral. Equally, all these angles in the corners, they're all bounded below. And so what this means is that when you look at this fellow here, and you go through and sort of look at this collection of quadrilaterals, you know that you can find some neighborhood around your quadrilateral which is contained in the union of all these neighbors. All right. And well, when you ask yourself, how large is this neighborhood is some epsilon k that depends on this k of how round your things are, times the diameter of the original quadrilateral. So you know that you can sort of establish this little collar around each quadrilateral, which is comparable to the diameter. And now, how does this help us? Well, the first way this sort of helps us, maybe intuitively what you want to say, is that you know that if you pass through this quadrilateral here, if you just nick the corner, then as long as your path was long enough, and if you sort of go back to the statement, you'll see that I have that condition. Maybe I'll bring it back up, is that if you just nick the corner even, then you know that if you look at how much time you spent in all the neighboring quadrilaterals together, you had to have spent at least enough distance to get in there through this color and then back out again. This is sort of where this k-roundness comes most fundamentally into play. Okay, so you know that you come in, you nick, you go out. This gives you some definite length. And so what you do is you sum over all the quadrilaterals that you intersect, so the length spent in the neighborhood of that quadrilateral. This can at most overcount each quadrilateral by a constant amount that depends on k, just because you know that by our k-roundness assumption again, every quadrilateral has a finite number of neighbors. So if you sum this over all the ones that you get hit by, you can overcount by at most the number of neighbors you have plus 1. And so at the end of the day, by performing this summation, what you get is that you get this sum of the diameters of the faces times this constant ck that depends on how many times you overcount it. And each time that you have one of these neighborhoods, you know that you pick up at least a certain little bit of length, this epsilon diameter k worth of length in the curve. And so by summing these things together, you get this expression. And I guess the little technicality I wanted to point out is, of course, that when I drew this picture, you have to assume that your curve begins and exits this little quadrilateral. And so it's the case here that you have to assume that your curve is big enough, right? If you have a tiny little loop, there's no way you're going to be able to bound the sum of the diameters in terms of the length, just because it could, just take some, think of length epsilon living entirely within one face. All right, but as long as it's long enough, you're fine. And so what this allows us to do is now you can take all the quadrilaterals that intersect a single circular arc and use the sum of their diameters to approximate the length. So this allows us to recover some of that geometric control that they had just where they assumed all faces were the same size, in this case where things are radically different in scale. All right, so that's sort of these two components. And then the third and final component we needed is we needed to know that we had a bound on the energy living at a certain distance. So we had an integral over the, so in the continuum argument, we had the integral over that ball of radius r of the gradient, which was this sort of semi-energy business we have here. And so what you need to know is you need to know that you can do that sort of thing in this discrete case as well. And well, I haven't gone through and sort of written out the details, but I can sort of just say that the argument works out the same way as before. In this discrete setting, we again have a maximum principle. That's something that gets held over as long as you're in the cases orthogonal quadrilaterals. So we have this maximum principle. And so you can again do this trick where you take the difference in the values on your discrete lattice and you push it out to this collection of quadrilaterals that intersect your ball of your circle of radius r. Once you do that, what you know is that you have this difference on the ball is at least as big as the difference between the 2 points on the function. You can connect them by a path. Again, you take that path, it will be contained in all the quadrilaterals we had before. So if you sort of mirror the argument, and what you see is that, well, here's where I have to take into account the boundary values. So I said before, you sort of leave them aside. And if you're careful, you just have to say, well, you look at the difference of the function, but then you sort of subtract off this maximum difference of the boundary. If the difference on the boundary is bigger than the difference that you're dealing with, then that's great. I mean, that sort of bounds the difference of the function already. So you assume you're in this bad case where your function differs by more than your boundary values do, where they intersect the ball. And well, you can iterate that, use that same argument I just said, to produce a lower bound on the semi-energy in terms of this difference and the radius. All right. And now, if you remember just sort of the last step of our continuum argument is we just have to go through and integrate this guy in R. And well, doing so yields the following equicontinuity estimate. So what you do is you fix your k, then you know there's going to be existing some constant c sub k. So if you take any pair of black vertices, again, this is one of those annoying things where the black and the white vertices don't really communicate, but if you take a pair of black vertices and some discrete harmonic function, then you have bounds on the modulus of continuity of this discrete function, which, if you look over here, is in terms of all things that you can bound on the continuum side. So you have this discrete Dirichlet energy. Well, we know that's bounded by what I said, by the continuum Dirichlet energy. This log term here is the distance between the 2 points, and then you have to take into account the lattice spacing, this m of q. And then you have the maximum over what occurs at the boundary. And well, all this is just telling you is that whatever your discrete Dirichlet problem is that you're trying to solve, or the continuous Dirichlet problem you're trying to solve, you now have the necessary control. So we had the three things we needed, right? We had this, well, I guess I claimed the first two. I claimed that we have this bound on the Dirichlet energy, and we have this bound on the sort of, well, we have this fact that the harmonic functions converge to harmonic functions, and this produces the equicontinuity. And so with this, just sort of with fairly standard arguments, you go through and you get to produce now this convergence result. All right, so that's a very quick, brief outline of the proof. Is of course, many bounds that must be done, but it's not that bad actually. And so that's what I'll sort of finish here with discussing a little bit about what this theorem means precisely. So the first thing, and this is what I want to sort of emphasize most of all, is that this condition, this k-roundness thing, is entirely local. So there's no global demands on your lattice at all. You just say the faces themselves aren't too bad. And so what this means is that you can get these, you can deal with these lattices that are sort of in many ways similar to the kinds of things that you get from the random maps, or indeed they are sort of exactly the kind of geometry you get if you circle pack a bounded degree random map. You can prove that you satisfy this k-roundness condition for some explicit value of k. That comes out of the sort of the ring lemma kind of techniques that live there. And so what this means is that, well, it's not good enough to deal with something like, the Brownian, the random planar maps, random planar quadrangulations, but it does sort of get us a lot closer to dealing with the sort of phenomena of drastically different scales. And now, just to sort of illustrate that, I mean, these guys here, it's just kind of a fun thing that I noticed I could draw these things, is that these are all just orthogonal quadrilateral lattices. And sort of as you can tell, there's kind of a method behind drawing what's going on here. And each one of these is in fact k-round for some uniform choice of k, no matter how finely you subdivide down into the little center there. So anything that sort of has this kind of feeling of regularity about it, just to sort of give you a concrete picture rather than just saying the word circle packing, if you have something that's this kind of regularity, you're fine. And this convergence result proves that if you have one of these lattices and the size of the largest rectangle or quadrilateral goes to 0, then you have convergence of your discrete harmonic functions to the continuum ones. All right. But as I've been sort of emphasizing here, we want to push further. And so I feel like it's a good thing to do whenever you have a proof that doesn't quite get you the result you want to say where the thing breaks. And well, it's in these two places that things need to be improved. Where this k-round condition, I really don't see sort of a way to move past it in any significant way. I mean, there are always little things, but nothing significant. And so, well, what you can do, the first thing to notice is that we had this thing here. We wanted to get that integral, which gives you the Dirichlet energy. And well, there's nothing at all stopping. If you're looking at a circle, your approximating path could be something like this, right? It just goes back and forth and back and forth and back and forth, where the quadrilaterals are very sort of long and skinny. So like this could be a quadrilateral, that could be a quadrilateral, this could be a quadrilateral, and so on. And well, as long as you have uniform bounds on that, you're fine. And so what I'm saying here is that when you go and approximate this thing by a discrete lattice path, nothing stops a discrete lattice path from being a very stupid bad one. I don't know how to say that there exists a good one. And so this stupid bad one could just keep using the long direction of every face. And so that means that when you go through and you approximate that semi-energy, you have this term coming from the difference along the endpoints here, and there's no real way that I see to eliminate that being the diameter. And so clearly in this case here that I've drawn, there's a better path taking just the other diagonals. And if you could say something along the lines of there always exists a better path, then you could get that semi-energy in terms of something else. But as it is, what happens is that when you take this difference along these things, you pick up this term as a semi-energy, this diameter term. Then when it comes time to integrate it again, well, you're integrating in this direction, so you pick up the diameter again. And so you need somehow just that your diameter squares and your areas are comparable. This already is a fairly strict requirement. It will eliminate sort of this proof outline working for random planar maps with unbounded degree. But also what you need to know from that argument that I gave in terms of saying that the discrete approximant given by the quadrilaterals that intersect your path having diameter squares comparable to length, then well, that's also another point where we very much needed this argument about the k-roundness, right? That's the one I sort of sketched out there with the quadrilateral in the middle. That I don't see a way of sort of producing this kind of thing that tells you that when you take all the quadrilaterals that approximate your given path, that they don't do it in some sort of horrible way where the diameters become unbounded, that this sort of just doesn't look like the path you started with. And well, sort of if you play around with these things, I don't see a way of getting around it that doesn't use this k-roundness condition. So I think there's something that needs to be done here to sort of push past this exact method of trying to work with things. All right, and so let's just end with a couple of questions here. The first one is, well, what I sort of talked about in the last slide, which is how can we actually use this to push further? So we'd like to, of course, develop this theory which is robust enough to work on these things that come from the uniform quadrangulations, these planar maps. This one doesn't quite fit that, it requires bounded degree. But can we push it further? And sort of, as a question that annoys me quite greatly, and perhaps someone can come up with a counterexample and I'd stop being annoyed by this, is that it's not known that any conditions on the lattice are required at all, to the best of my knowledge. So, is there a sequence of lattices and Dirichlet problems on those lattices so that it does not converge? The discrete solution of the Dirichlet problem does not converge to the continuous one. And this, to the best of my knowledge, and Skopenkov makes a similar result, so I think this is sort of is something that people have thought about, is that I don't know of any example of lattices, no matter how distorted, where this does not hold, as long as this minimum edge length goes to 0. So that's very annoying. When you go through and you work very hard and you push these theorems just a little bit epsilon further, you say, well, you only have to care about the local geometry. We don't even know if you have to care about the geometry at all. And so it'd be very nice if you could have some enemy that we could point to and say, here's some sort of, here's a sequence of lattices that are bad. Any theorem we have cannot hold for these. We currently don't have that. And then third, of course, that this talk contained only probability and motivation. And so it's my hope is that if it contained probability and motivation, it can be used to motivate probabilistic results. And so something that I'm currently thinking about a little bit as well is that what can be done to show these things? Like say, can we show things about loop ratio random walk converging to SLE2 on these kinds of horrible lattices that we expect to be getting out of these quantum gravity questions? All right, and well, that's that. So thank you for your attention. And again, I'd like to say happy birthday to Greg.
All right, are there any questions? Yeah, you've got.
So, how about Neumann conditions reflecting these lattices?
So I wish to do that as well, but I have not worked on those kind of questions. But yes, they are, of course, very relevant.
Chris?
So I actually have a remark on the Neumann condition.
Mm-hmm.
And there's a weird example of a fractal domain where simple random walk, one would have to be careful about that approximation, does not converge to reflected Brownian motion.
Mm-hmm. Mm-hmm.
But this is actually subtle because you can define that approximation in two different ways. It converges in one situation, doesn't converge in the other approximation. And basically, I'm not saying that this would answer your question, but perhaps you could get some inspiration from
yes, there are these examples. Now I'm going to point out sort of why these examples don't necessarily give you what you want. It's this expression here when you look at the Dirichlet energy. And the reason I bring this expression up is because you said that as you wanted a simple random walk on these lattices, but the notion of harmonicity I'm using here is not the simple random walk. It's a random walk with weights, which are given by the geometry. And the weights are given by these terms here. These are the sort of the weights on your simple on your random walk. And so indeed, there are many examples, I know of a few as well, where sort of simple random walk on some perfectly reasonable looking lattice can behave completely unlike, say, a Brownian motion in the scaling limit. And these are places, of course, where I went and I looked for these kinds of things. But it's the fact that these sort of weights here, these weights are built exactly to kill those kinds of examples. And so I guess all I'm saying is that the ones along those lines that I've looked at have not yielded these bad examples, but they are indeed a very, very good place to go looking for them.
In your example, that this discrete energy converges to the continuous one, right? The Dirichlet form, right?
Yes, yes.
If you observe in this way, and the limiting Dirichlet form has nice properties like have Poincare inequality and so on, right? Mm-hmm. Then you can do this. Using these Harnack type inequalities, you can control this equicontinuous properties in a rather wide framework, I guess. Mm-hmm. That's probably.
So I mean, in that kind of framework, yes. Then the problem here is that when you try and do this, so exactly as you say, if you have this sort of convergence on the Dirichlet form level, where you want to say then it works. So one could view this result in a certain way. I mean, it's not of course the way I talked about, but this is sort of the convergence of the Dirichlet form that needs to be shown. But yes, limiting Dirichlet form is nice, and we'd like to know that all those sorts of arguments you'd like to do in the continuum still held here. Many of them should, but I don't know. I don't think. Yeah.
Any other questions? Okay, so we've now got a coffee break until 3:30. So if we just thank the speaker once more.